Hi guys, my name's Jenny and my project was on the remote sensing of winter cover crops in the Central Coast region of California. So to give a bit of background, the reason I'm focusing on the Central Coast is that it's a key agricultural region for our country. It's often called the salad bowl of America due to its leafy green production, and it represents a $5 billion a year industry if you also include neighboring San Luis Obispo and Santa Barbara counties. And it has year-round production, often 2 to 3 crops on a given field per year. But with this really productive agricultural system comes a lot of negative environmental impacts. 75% of the land surrounding the major watersheds of the region is used for agriculture, and 51% of all the nitrogen applied in the region is eventually leached into groundwater supplies. And that's a major source of fresh water for the region. And nitrate polluted water can lead to higher risks of thyroid cancer, as well as a lot of other negative health impacts for farm workers in the region. So this is also a major environmental justice issue. So cover crops are a valuable tool for mitigating a lot of the negative environmental impacts that are associated with agriculture. And what cover crops are is normally after fall harvest, over the winter season, fields are left bare. And cover crops are planted as an alternative to bare fields, because they have a lot of environmental benefits, such as decreasing nitrate leaching, improving overall soil health, and actually can increase the amount of carbon soils can store, along with a lot of other environmental benefits. And examples of some cover crops are clover or rye, radish, mustards. And cover crops are really a necessary part of a sustainable crop system. However, we don't have any quantitative or spatial data available on cover cropping in the region. So remote sensing can offer a really efficient way of gathering this data. And what remote sensing is at its core is observing from a distance. And so that often means using satellite imagery. And NDVI is a common index used to detect vegetation. And it takes red and near infrared spectral properties of satellite imagery, which is based upon the chlorophyll content of the crops or vegetation. And it can detect crops that way, as well as distinguish between different crops. So what it can do is it can look at the satellite imagery of campus, and it can say which pixels have vegetation versus which pixels are cement or don't have any vegetation, based off of the NDVI values of each of the pixels. So using remote sensing can be super helpful for monitoring agricultural land, because it can capture huge swaths of land in a short period of time, which is really beneficial for agricultural land, which is changing really quickly. Cover crops are only in the ground for a very short period of time, so it allows you to capture huge amounts of data in just one sweep. But there's also some challenges, especially in the Central Coast, because regions typically where cover crops are studied with remote sensing don't really have any winter cash crops over the winter season. So basically, they just look to detect vegetation over farmland in the region, and if there's vegetation detected, it is assumed to be a cover crop. Versus in the Central Coast, there's a lot of winter cash crops planted over the winter season. So you have to be able to distinguish cover crops from other winter cash crops like strawberries or artichokes. So my study seeks to find out how much agricultural land in the Central Coast is using cover crops over the winter season. And to answer that, I wanted to look at the spatial distribution of cover crops, as well as see how accurate the classifying techniques I develop are at actually being able to remotely sense cover crops, given the significant challenges at remotely sensing cover crops in this region. Okay, so getting into the methods, I use Google Earth Engine, which is a cloud-based geospatial analysis tool that's free to use. And then I use Sentinel-2 satellite imagery, and I decided to use Sentinel-2 based upon its spatial resolution of 10 meters. And what that means basically is each pixel of imagery is equal to 10 square meters on the ground. And then I wanted to compare a random forest and cart classifier so that I could have the results of 2 classifiers to see which one would be more accurate. And then I limited my classification to farmland boundaries, which I obtained from county offices. Yeah, so the way that these classifiers work is you have to be able to train the classifier with ground truth data for it to then be able to scan an image and classify. So a classifier is not going to know what bare soil or strawberry fields or cover crops look like until you tell it what it looks like, what NDVI values are associated with strawberries or associated with cover crops. And then once it's trained, as I said, it can scan the image and it classifies each pixel. So a good portion of this ground truth data is used to train the classifier, but another portion is used to test the accuracy of the classifier. So once the image has been classified, you then can compare the results of the classifier to these testing points and say, this is what the classifier says is there, but what does the ground truth data tell us is actually there? Was it misclassified, or was the classifier right in detecting that it was either bare soil or cover crops in that location? So basically what I did was I went around the Central Coast and I collected ground truth data by identifying the crop types in different fields and then associating that with a GPS coordinate to the satellite imagery. Okay, so the first thing I did was I ran a threshold classification in order to distinguish perennial land versus non-perennial farmland. And what that means is basically perennial land is crops that are planted year round. So there'll always be vegetation in the ground. So artichokes, apples, etc. will always have vegetation in the ground. Versus non-perennial land is land that had a crop at some point, and then it's taken out sometime in the year, there's bare soil, and then a new crop is planted, such as a cover crop. So to figure that out, I looked at from June 15th, 2020 to January 15th, 2021, and I took the minimum NDVI over that time, and I created a 0.2 NDVI threshold. And 0.2 is kind of a common cutoff point where anything above 0.2 is likely to be vegetation, where anything below 0.2 is likely to be bare soil. So I basically said, if throughout this time period, did at any point it drop below 0.2, which indicates that at that point there was bare soil in the ground, which means it'd be a non-perennial crop, versus perennial crops will have never dropped below 0.2 because there will always have been vegetation in the ground. So then I took the non-perennial land and I created new vector boundaries, which I then limited my subsequent classification and analysis to those new boundaries. So this is an example of an artichoke point, which is a perennial crop. And you can see from June to January, it never once dipped below that 0.2 threshold. Sometimes got close, probably associated with harvest, but it would be classified as a perennial, which it is, based upon the fact it didn't drop below 0.2. Okay, so my crop classification, I looked at the winter time. So I looked at December 15th, 2020 to January 15th, 2021. And I took the median NDVI as well as median blue and green spectral bands. And for each class, I used 80% of my training point or my ground truth points to train the classifier. And then I used 20% of my ground truth points to test the accuracy of the classifier for each class. And the classes I used were bare, strawberry, cover crop, and then all the other crops I found were in an other crop class. And so I ran random forest and cart classifiers to compare the results. And then I clipped the classification to non-perennial boundaries that I had created with that threshold classification. So this is an example of a portion of my script that was used to classify. Google Earth Engine uses JavaScript. So this is kind of an example of what I was working with. And then on to results. So this is the perennial versus non-perennial classification. The perennial land is in purple. And then in the non-perennial land, I just ran a vegetation versus bare soil classification. And you can see that the threshold classification had an 84.2% accuracy at distinguishing perennial versus non-perennial land. So this is the cover crop classification where I classified bare crop, perennial crops, strawberry, and cover crops. And you can see that random forest had the highest accuracy with 86.7%. So that's what I used to make the maps and calculate the areas. And you can see that a significant portion of the farmland is bare over the winter time, 58.1%. But most importantly is we found that 72.6 square kilometers is used for cover crops, which represents 4.8% of the farmland in the region, which is pretty consistent with literature, which estimated that it was around 5% or less was cover cropped in the region. Okay, so what does this mean? The high areas of the bare fields indicate a need for policies that can increase and incentivize cover crop adoption, because as we see, there's a large area of bare soil and a very low amount of cover crops. So there's a large opportunity to increase cover crop adoption. And we also found out that the region poses considerable obstacles when using remote sensing to detect cover crops in the region, and that those need to really be accounted for when we're designing a remote sensing technique. And then future directions is we can use object-based segmentation, which object-based segmentation basically detects edges of fields. So it can detect the edge of a field and then create a boundary around that field. And then you can take the average of the classification results of that field. So some of the fields in this image to the left you see are pretty much entirely bare, but there's a little bit of noise within the field of a vegetative class. And what it does is it takes the average of that field, so that would be bare, and then it classifies the whole field as bare, and that can improve the accuracy. We can also do cover crop monitoring for additional years to see how cover crop levels are changing over time, especially in response to different policy measures that are implemented, to see if cover crop adoption levels are increasing. So that's it. I want to give special thanks to my mentors, Professor Timothy Bowles and Jennifer Thompson, as well as my SBUM 175 team, and then Ariel Adair and Kate Libby for help with the ground truth data collection. Thank you.